Okay, thanks everybody for joining us today for another installment in our webinar series. My name is Matt Donovan, and I'm the Renewable Energy Specialist here at Catalyst Sales. And today's presentation, is continuing on the trend of the electrification of everything, and I'll be talking today about battery storage. Here's an overview of what we're going to be discussing today. I'll start with a little background on us here at Catalyst, then move into a history and a bit of the science on batteries. I'll talk briefly about electric vehicles, then batteries today. Then we'll talk about some of the applications that battery storage has in the real world, and we will finish off there. So our story here at Catalyst, for those who don't know, we are an electrical sales agency with over 15 years of experience in bringing products into the Atlantic Canadian market. And we have a particular focus on sustainable technologies and renewable energy. So what we do is connect global manufacturers of electrical products to local markets. And that is what our focus is what we do best. Finally, I'll talk about the electrification of everything. So this is a trend that we've discussed in a number of our webinar series. And there's a great focus worldwide on shifting away from fossil fuel-based energy to electric energy. And you're seeing it across a number of different sectors in transportation with electric vehicles, in space and water heating, in energy generation, such as our solar and wind generators, and then finally, with today's focus, battery storage. For the history of batteries. So for those who don't know, there's actually evidence of batteries being used as far back as prehistoric times. So archaeologists found an artifact in modern day Iraq, which is referred to as now the Baghdad battery. And it consisted of a ceramic jar, a tube of copper, and an iron rod. And the archaeologists theorized that this device was used to electroplate gold onto other metals. But moving ahead in history, we find Benjamin Franklin, who's well known for his studies in electricity. He's actually, his key and kite experiment with the lightning is very well documented and shown in that image there on the right. But he's actually known for coining the term battery when he joined capacitors in parallel. And finally, we have Alessandro Volta, who about 50 years after Benjamin Franklin created the voltaic pile by stacking copper and zinc discs separated by moist cloths that were soaked in brine. And this is known as the first wet electrochemical battery and really kickstarted the movement and research into this technology. So the science of batteries, what a battery does is that it stores electrical energy as chemical energy. And how it does this is by allowing electron flow from one side of the battery, the anode, to the other side of the battery, the cathode. And this is what creates that electric current, which powers our devices. Now, the electron flow through the wire also needs to be balanced by a corresponding movement of ions. And so this is where the electrolyte solution comes in and why our pal Alessandro Volta had that wet cloth soaked in brine. So the electrolyte, sodium, potassium, lithium, ions such as that can be used as the electrolyte solution in a battery. And then in charging, the opposite movement of electrons takes place, but this needs to be done by the introduction of a forced electric current to reverse that electron flow and recharge the battery. Now, moving on from Alessandro Volta, there was quite a bit of work being done on electricity and on battery storage. And in 1859, French physicist Gaston Planté discovered the lead-acid battery, which was also the first rechargeable battery ever discovered. And it's, in fact, the lead acid battery has had such a longevity that we still see it today. It's actually makes up the majority of battery storage in the world is still lead acid. Now, lead acid has its merits and its benefits, such as having a high power to weight ratio, which makes it ideal as a car starter. So your car battery, it would be lead acid, but it also has some negative sides. So it has a low energy to weight ratio. And if anybody here has ever picked up a lead acid battery, you'll know what I'm talking about. You have to stack quite a few electrical links in there to get a decent volume and voltage in there, which contributes to very high weights of these batteries. And I mean, despite these drawbacks, large format lead acid batteries are still commonly used today as backup power supplies. And then moving on from lead acid, in 1992, we saw the lithium-ion battery become available commercially. And this also corresponded with the rapid advancement of portable electronics. We would not be where we are today without the lithium-ion battery. So I mentioned the the energy to weight density for a lead acid battery. Well, the lithium-ion battery solves that problem. It packs quite a bit of energy into a much smaller package, which is why portable electronics have become feasible. And a lot of research has been done and is currently being done on lithium ion. So there are quite a few different chemistries available for this type of battery. So I'll note a couple of them here. So first of all, we have a lithium polymer cobalt oxide battery, which has high energy density, but it does present safety risks, and it had some high profile negative publicity when the Galaxy Note 7 was brought to market and found that it would, due to a manufacturing defect, it would spontaneously combust. In fact, it's still barred from entering airlines today. And obviously those phones were recalled by Samsung, and that manufacturing defect was corrected. But nevertheless, this battery chemistry does have its issues with safety risks. And so a similar but slightly different battery chemistry, the lithium nickel manganese cobalt oxide. You see this type of battery in the LG Chem or the Tesla Powerwall, and it offers high energy density and stability, but the use of cobalt does increase the risk of thermal runaway, as we saw with that Galaxy Note example. The final battery chemistry I'll touch on is the lithium iron phosphate, which is a newer battery chemistry, which makes it a little more expensive than others, but it does have its applications, and a company called Sonnen, which I'll mention later on, uses this type of battery as a home battery storage unit. And so some of the advantages that this chemistry offers is greater safety and thermal capabilities, so it has a longer life. Since they don't generate heat, they also require very little cooling and mean they can be installed in more unique indoor applications. Now I'll talk about electric vehicles. So a lot of battery advancements have been made due to the focus on electric vehicles. These cars would not be possible today without the lithium-ion battery. Thanks to the energy to weight ratio lithium-ion offers, it makes them ideal for transportation and much more usable over its predecessor, the lead acid. So the image on the right shows a cutaway of the battery pack in a Nissan Leaf, and you see the number of battery packs that are stacked in order to make up that total storage capability for the car. And the battery does make up a significant cost of the electric car. So the cost of electric vehicle batteries has fallen since 2010, about 87%. So back in 2010, you were paying about $1,700 per kilowatt hour of storage. And it's predicted that by the end of 2021, that cost is going to have fallen all the way to $100 per kilowatt hour. And if you've heard me speak on electric vehicles at all, you'll know that the cost of electric vehicles is falling, and it's starting to levelize with combustion cars, and the price of batteries falling has a big part to play in making these vehicles commercially viable. And then finally, the size of a battery pack in an electric car ranges from about 20 to 100 kilowatt hours. All right, so battery storage today. The three products pictured there I did mention earlier, the Tesla Powerwall, the Sonnen battery, and the LG Chem. And manufacturers like these can't produce lithium-ion batteries fast enough. The demand for small lithium-ion batteries is well known for portable electronics, but larger batteries for electric vehicles and for home storage units are becoming more and more popular today. So these products are all marketed as smart home lithium-ion batteries, and they're putting massive amount of resources into developing bigger and better home batteries. An example of this, so the middle manufacturer there, Sonnen, was actually acquired by Shell recently. So pretty big dollars being thrown around in this space, and we're going to start seeing them become more and more common. So one thing these companies are all working to do is integrate their batteries with smart home technology. So it's also theorized that combining these home units with intermittent generators such as wind or solar, you can really maximize their usage in a home. So one way that battery companies are making this feasible is through AC coupling. So how this works is you have your DC direct current electricity flowing from either your solar panels or your wind generator to a inverter. And this, after the inverter, you have your alternating current, which can go to your home loads, or it can go to the battery where it can be stored once again as direct current. Most solar batteries nowadays also offer an auto transfer switch so that when the grid goes down, your home can still be powered by solar. Some other benefits that are offered by tying in battery storage to the home. You can have precise control of your electric consumption. You can utilize time of use shifting for places that offer time of use rates. You can maximize your self-consumption of renewable electricity, so you can make sure that all that solar on your roof is powering your home. You can also control demand response and utilize peak shaving capabilities. And of course, that backup power that's offered during grid interruptions. I mentioned earlier the cost of lithium-ion batteries when I was talking about electric vehicles, and how this cost has fallen 87% since 2010. So high demand for applications like electric vehicles and home batteries is driving production, and this mass production is helping drive this cost lower. Also, new and improved battery chemistries are driving this cost down and making it more and more feasible for the average homeowner to get access to this type of battery. With that said, lead acid is still the cheapest upfront option for battery storage, with costs as low as $150 per kilowatt hour. However, when you factor in space requirements, energy density, charge cycles, and other factors like warranty or the ease of use for lithium ion in terms of smart home integration, the case for lithium ion batteries begins to strengthen. But I mean, if you look at the price per kilowatt hour graph there on the left, and now these are in Australian dollars, but you get the sense that those lithium ion home batteries are quite a bit more expensive upfront than lead acid. Now, as that cost falls and you factor in all those other factors that I mentioned, you'll start to see the case for lithium ion strengthen. I want to talk now about some future applications of battery storage involving this topic of demand-side load management. Now, you may have heard this term before, and there are some very exciting applications at both the utility and residential level which utilize this technology. So, three important applications that I'll mention are meeting energy supply shortages, hedging price volatility, and maintaining grid stability, all three of which I'll go into greater detail. Starting off, we'll talk about peak shaving. So this is one great advantage that battery storage can offer. Peak demand charges can make up the majority of an electric bill for homes, businesses, and industry alike. Actually, according to the National Renewable Energy Laboratory, energy demand charges can account for up to 70% of a customer's utility bill. And so for those who don't know, demand charges are applied once a customer has reached a certain load on the grid. So how peak shaving can counteract this, and is most effectively done when combined with an intermittent generator such as solar. But what you do is you program your battery storage system to guarantee that no power is drawn from the grid above a predetermined threshold. And so this negates those peak demand charges that you'd see without a battery or energy use strategy. And then when the demand goes back down, you can recharge the batteries utilizing that energy from either your intermittent generator or from the grid. So another interesting and powerful idea involving battery storage is solar microgrids. So an example of this is the Sonnen community. I mentioned Sonnen earlier when talking about some of the current home batteries available. And so what the Sonnen community is members provide a share of their battery storage to the public grid. And so this is especially powerful because what it does is it allows users to utilize intermittent generators and renewable sources as much as possible. Now, obviously the sun's not shining all the time and the wind's not blowing. So when members of the community are overproducing, they can send that excess power to other members of the community. And then when they themselves are in need of electricity, they can benefit from drawing energy from the community grid as well. And combining ideas like this with intermittent generators is going to make our transition to renewable power that much more viable. So another type of energy storage, and it's not quite the same as battery, but I will mention it quickly, is pumped water storage. So how it works is pumping water from a lower to higher elevation and storing that water as gravitational potential energy until needed. When the energy is needed, water is released through a turbine and electricity is generated. So one of the biggest benefit that this offers is helping to offset the solution or the problem of peak demand. So rather than ramping up production or bringing on a peak power plant and really upping the cost for consumers, you can use this pumped water storage to send electricity to the grid when needed most. So the startup costs for a pumped water storage facility are often much lower than those for a peak power plant, and it helps ensure grid reliability and stability. Now, it must be mentioned that there is a net loss of efficiency using this type of technology, and that net loss equates to about 26%. Despite this, there is still pumped storage facilities here in Canada. There's one in Ontario currently, and there also is plans in the work to build one out in Alberta. All right, so another application of battery storage at the utility level is the idea of the virtual power plant. So this is a concept that comes up frequently when discussing future applications for battery storage. And how it works is it refers to the storage of electrical energy in utility scale batteries as a means of stabilizing the grid. So I mentioned earlier about those intermittent generators, your solar and wind energy. Now, these generators are intermittent for a reason. The sun's not always shining, the wind's not always blowing. But if you can pair battery storage with these intermittent generators and maximize those times when you are overproducing energy, you can store it for times when it's needed most, when those intermittent generators aren't operating. Another great advantage of something like the virtual power plant is that it can also reduce dependence on those peak power plants, which I mentioned in the pumped storage slide. So peak power plants really drive up the cost of peak demand electricity since their startup costs are so much higher. And so a utility scale battery that can be called upon when the grid needs it most can really help provide price stability and grid reliability in areas that rely on intermittent generation. So virtual power plants ensure that any excess energy from intermittent sources can be stored for later consumption when needed most. An example of so there actually is an example of this type of facility being constructed. There's a collaboration between Mitsubishi and Eneco in Germany. So they're building a 50 megawatt battery or 50 megawatt hour battery near Denmark, and it's going to be utilizing the wind generation capabilities of Denmark to power that virtual power plant, which can be called upon and can help offset those peak demand charges, as I mentioned earlier. And so another type of energy storage is the thermal storage unit. Now, Nova Scotians would be familiar with this. It does get you access to time of day billing. So how it works is you consume electricity at night when it's the cheapest, when the grid is at the least amount of demand, and you use it to heat these clay bricks inside of the unit. Then during the day, you distribute heat through your house so that your electric baseboards aren't racking up peak demand charges during those peak hours. So right now, thermal storage units are the only method to get access to time of day billing here in Nova Scotia. But I expect that time of day use to become available and the norm for homes with smart battery storage. In fact, in Ontario, you can actually get access to time of day billing with just the addition of a smart meter. All right, so all of these technologies that we're talking about and these ideas and theories really mean nothing without some real world data and examples to draw upon. So one such example is a Utah apartment community that's combining rooftop solar with over 600 of those home battery units that I've spoken so much about. And those 600 units total 12.6 megawatt hours of storage. So this community will allow the utility to buy power from the apartment's batteries during times of peak demand. So really it's functioning in a similar manner to that virtual power plant that I spoke about earlier. Rocky Mountain Power is using it as a trial, and as such, the utility actually owns these batteries. But the consumers are still benefiting because they have access to backup power and a fully green home. The building is designed to be entirely net zero, meaning that all of the energy for this entirely electric building, mind you, will come from solar on the roof. Another case study that I looked into was up in Elmsdale here in Nova Scotia. So a utility scale battery has been installed at the Elmsdale substation, in addition to 10 Tesla Powerwalls that have been installed in nearby homes. So the substation batteries charged via wind turbines, which in turn send power to these 10 Powerwalls. So the purpose of the study is to test this combination of intermittent generation with battery storage as part of the overall focus on shifting to renewable power. For those who've been on previous webinars, you know Atlantic Canada's current electric profile is quite dirty in comparison to the rest of Canada and also to places around the world. So initiatives like this are extremely important for us as Nova Scotians and Atlantic Canadians to help reduce our carbon footprint and shift to a more sustainable energy profile. Another study being done is over in Shediac, New Brunswick. So Natural Resource Canada has committed $5.7 million for a green energy initiative in Shediac. The trial for these new technologies is being developed between NB Power, Siemens, and and Natural Resources Canada. And they're testing various smart home products such as thermostats, solar PV, smart water heaters, and of course, in-home battery storage. So overall, the barrier at this point for widespread adoption of this in-home battery storage is the cost. But as I mentioned before, developments in this technology, thanks to electric vehicle research and these in-home battery units, mean that this cost is falling. So some of these initiatives being undertaken, may seem far off and unrealistic. You always hear about some of the adoptions in Germany and Norway and Sweden, but these are in our backyard right now, and maybe some of them will fail, but I truly believe that it's only going to lead to future and more refined experiments, and we really are on the cusp of widespread adoption. Because we're seeing similar progress in electric vehicles, solar, and now finally battery storage. So some frequently asked questions about battery storage. So what is grid stability? So grid stability refers to the ability of utilities to respond to fluctuations in demand. So from the utilities perspective, battery storage is great because it allows them to quickly respond to these changes in demand. Further, as residential batteries become more widespread, it's going to allow homes to avoid accessing the grid at all during these peak hours, which will benefit homeowners in terms of cost, and it'll also benefit the utility in terms of the strain on the grid. Another frequently asked question, if I have solar on my roof, will I still have power when the grid goes down? So unfortunately, the answer to this question is no. And currently, net metering still is the best way to get access to solar as a homeowner. But the only way to guarantee that you'll still have solar power when the grid goes down is through battery storage. And this is mostly because of the safety reasons. We can't have power flowing out to the grid during an outage. And finally, those time of use rates. So can I get time of use rates with a battery storage unit? So right now, you need that thermal storage unit in Atlantic Canada to get access to time of use billing. But I expect that to change very soon. Already in Ontario, you can get a smart meter installed, which gets you access to time of day billing. And in places like California, time of day billing is the norm. And so as that becomes available to Atlantic Canadians, the merit and viability of things like battery storage and solar just increase all that much more. So thanks so much for joining us today. You can get in touch with us at these sources. Also, if you have any questions, please feel free to ask them in the chat or reach out to me via email.